Hello guys, today we're going to be exploring the concept of Taylor series. We're going to do this by going over and explaining in detail one of the FRQ questions from the 2009 Calculus BC exam. Without further ado, let's jump right in. So, the first question is asking us to write the first four non-zero terms and the general series of e to the x minus 1 squared. Well, how can we do that? Well, you can recognize that this is very similar to the identity that e to the u is equal to this series. So what we can do here is we can substitute whatever this power is, right? Because this is similar to this property, and we can substitute u as x minus 1 squared. Hopefully you see that. Alright, now we can simply just put whatever we substituted u as, right, because that's what is in the power of e, and write that in our series representation. Okay, so now that we have the series, how do we write the first four terms? Well, a series is essentially an infinite amount of terms adding to each other, right? So to get the first four non-zero terms, we just have to keep adding until we get four terms. So we can just keep incrementing n until we get that result. So let's do that. So first term is n equals 0. So we can just, there's an n here. So we can just, the first term is 0. So we can put n as 0. 2 times 0 is 0. 0 factorial is just 1. And we can keep on going until we get four terms that are not 0. So let's just write that out. Alright, now we have the first four non-zero terms. I mean, all of these are not 0, so you can conclude that. So how do we find the general series? Well, we wrote these first four terms based on this series in terms of n, right? This series in terms of n. So the general series would just be this, because that's what it is in terms of n. So we can just simply write this. This is just to represent an infinite amount of terms all the way up to n, however many terms up to the nth term, and that is your general term. And this is your first four non-zero terms and your general series. And that is the solution to this first problem. Alright, now let's hop into the second problem. My apologies for the slow pen. Alright, now we have to write the first four non-zero terms and the general term for f of x. Similar to the last problem, but with this function, with e to the x minus 1 squared. Well, we can recognize that we already just solved the Taylor series for e to the x minus 1 squared. This is a simplified version of it I just wrote out beforehand. So how can we write the first four terms? Well, we can just, because there's already terms here, we can just use this and algebraically manipulate it with whatever's in the function, right? So let's do that. So we can write 1 plus x minus 1 squared all the way to what we have. Alright, so now we substitute e to the x minus 1 squared, we can complete the rest of the function. Okay, so now what? Well, we already have these terms, right? So we can just simply do some algebraic manipulation. This cancels out, and this can be divided among all the terms in the numerator, okay? So we can rewrite this as 0 because 1 minus 1, and this becomes 1, right? X minus 1 squared, divide by itself. And we can just extract 2 from each exponent, and we get something like something like this. Okay, so we have the first 4 non-zero terms, right? I wrote a 5th term because this is a 0, so this doesn't actually count. So we can exclude that, right? So what about the general term? Well, it's a little more complicated. We can still say that x minus 1 to the 2n is the numerator because it's incrementing by 2 for the exponent. But the bottom is a little bit different. Because we excluded this 0 here, we start at n plus 1 for the denominator. This is 2 factorial, 3 factorial, this is 4 factorial, right? But here, this is actually 3 factorial. This compared to 4, this is 2 compared to 3, etc. Because we excluded the first term, we start at n plus 1 factorial. So because of this, we have to write n plus 1 factorial on the bottom. And we don't want this again, so this will be your answer to this problem. Alright, let's move on. So now we have to find the interval of convergence for f of x. Okay, cool. To use the ratio test, we know that we have to use this property, okay? So how do we implement this property with x to the n, x sub n plus 1? Well, x sub n plus 1 is essentially just replacing the n with n plus 1 in this series. So let's write that out. So limit as n approaches infinity of x minus 1. We substitute n with n plus 1 here. So the distributed value would be 2n plus 2. And on the bottom we n plus 1 factorial. So that would be n plus 2. And this would be all over. I will write it as a form of multiplying because it's more ugly if you just write in all division. So divided by n plus 1 factorial all over x minus 1 to 2n. Okay. So how do we go from here? Well, we can rewrite this. We can separate what we need because in order to solve this, we have to cancel out some terms. So for x minus 1, we can actually separate this. So we have it both x minus 1 to the 2, and on the bottom, we can rewrite n plus 2 as n plus 2 times n plus 1 factorial. Because the factorials is essentially just n plus 2 times n plus 1 times n all the way down to 1. So hopefully that makes sense. And finally we have x here. So we can simply cancel this and cancel this, okay? So what we're left with is limit as n approaches infinity of absolute value x minus 1 squared, right? Because we're centered, and n plus 2. Now this limit is 0 because the denominator keeps increasing. So what is the interval of convergence if this is 0? Well, if it goes to 0, then that means that the convergence is based off of a constant. So if it's a constant, then that means that it converges for all real numbers. So this means if it converges for all real numbers, then the interval is just from negative infinity to infinity. So that would be your interval because it covers all real numbers. And that is your solution to this problem. Alright, let's move on to the final part of this problem. We want to determine the inflection points for f of x, which we already found again. So how do we do that? Well, we know that to determine the inflection point of a function, we need to take its second derivative and determine when it's 0. How can we find the second derivative of this series, the function given its series? Well, we can just derive the terms itself. So let's start that. So if we derive the terms, we can derive 1, which is 0, right? We don't need to write that. And we can use the chain rule here. And this power becomes 1, so we ignore it and multiply it. the derivative of the inside using chain rule, which is 1, so we can also ignore that. And we can do the same thing here, all the way. Okay, now let's derive it again because we need the second derivative. This becomes 1. This becomes 4 times... Okay, so now we have the second derivative. So how do we find the inflection point when there's no 0, when there's no place where f double prime of x is 0? Well, if there's no place where f double prime of x is 0, then that means there's no inflection points, because all of these are non-negative terms, right? So there's no inflection points. And that is why, because if there's no 0, then we can just conclude that there's no inflection, because if it's always positive, then it concaves up, and vice versa for negative. So that is the solution to this problem. If you need more help understanding, some helpful resources that cover more in depth of the Taylor series concept include this set of Khan Academy videos, which is really helpful in my opinion, along with Organic Chemistry Tutor. He does the sets on the video and explains them, and that's how I usually learn if I don't understand. And finally, if you want to do some practice problems yourself, this site called Math Library Texts is also really helpful if you want to do some on your own. And that's it.